This lecture is about the least squares principle. So the main goal of this lecture is really to understand where the OLS formula comes from. Remember, the OLS formula gives us the slope and the intercept of a linear trend line that fits the scatter plot of data quite nicely. It turns out that these formula are from a principle called the least squares principle. So the setup is as follows. I have data and observations. I have an x variable, I have a y variable, and my view is that the x variable in some sense, at least partly, determines the y variable. I also have a linear trend line. Note that in this case, it's not necessarily the OLS trend line. It's just a trend line, b1 plus b2x. That means that b1 and b2 are now just arbitrary constants, not necessarily equal to the values that we get from the OLS formula. We know that the residuals, the distance, the vertical distance between the actual y and the trend line, will depend on the trend line. So it will depend on b1 and b2. Let's illustrate this with some data. Here's some data on an x variable, the number of hours studied by 9 students, and the y variable, the result on the final exam. The point now is that I am going to define an arbitrary trend line, not necessarily the OLS one. So I'm going to define a B1 and I'm going to define a B2. And I'm just going to set arbitrary numbers here. Let's set the intercept to 0 and the slope to 1. Now I have defined a trend line. A trend line's intercept is 0 and the slope is 1. So based on this trend line, I can find fitted values. So let's name these cells. Also, let me show you the name manager because it's quite useful. In the formulas, you have a name manager. So if you have already defined some names, you can just delete these in case you want to reuse them for something else. You can also use the name manager to define new name cells using the new here. I just find that a little bit inconvenient. I think it's better to just use the name cell like this. We name this B1 and we'll name this B2. So let's do the fitted values, and these are not, I reiterate, the OLS fitted values because they are not based on the OLS B1 and B2, but we can still do fitted values. So it's B1 plus B2 times X value. And since I've just done arbitrary B1 and B2, the fitted values will be quite terrible. These are the fitted values. If we look at the scatter plot of the fitted values and the trend line then, with X and with the Y data, we'll see that it's pretty bad. If you imagine a straight line through the orange blobs, the fitted values, that's the trend line. And the blue dots are the scatter of our data. And in this case, the trend line is obviously horrible. But we can try and fix that simply by changing the linear function that represents the trend line. Since the entire trend line is above the data, we need to take down the intercept to take down the entire trend line. So let's take it down about, I don't know, 40 units. That will make it look much better. Probably a little bit more than that, 50 units. Maybe even more than that, 60 units. So now it looks much better, but we can still see it's not that great because the trend line seems to have a slope which is much larger than the slope of the blue dots. So we can take down the slope to, let's say, 0.8. And if we do that, then we have to increase the intercept because now that is too small. So we can keep on playing like this, trying to figure out B1 and B2 such that we get a nice fit, but the problem with that is that we don't have any criteria for saying that one fit is better than another. We are simply relying on our eyes to tell us that, well, this fit is terrible and this fit is a little bit better. So we need a criteria for saying that a fit is better than another fit, or a trend line is better than another trend line. Well, we have previously discussed that RSS is a measure of fit. A large RSS means that the residuals on average are large in absolute terms and that the fit is poor. So we want the RSS to be small, and a small RSS represents a small fit. So maybe we can use the RSS value to say whether one trend line is better than another. So let's calculate RSS in this particular case. So I am adding then the residuals, and again, to emphasize, not the OLS residuals, just residuals. But the residuals are still defined as the deviation between y and the fitted y. And I copy this down, and that will give me the RSS easily by just doing sum SQ of these guys. So let's highlight this number because this is the one that we will now use when comparing two different trend lines to say which one has the best fit. So I'm going to just highlight this a little bit so we can focus on that. So right now I'm considering a trend line with an intercept of -40 and a slope of 0.8. Now, would I get a better trend line if, for example, I increased the intercept to -35? So if I increase this to -35, we can just look at RSS. It's 558.68 now, and if I change it to -35, it goes to 345.68. So that is an improvement. This represents a better trend line, having an intercept of -35 compared to -40. So now I actually have a measure, so I can see if I'm going in the right or in the wrong direction, trying to find a nice trend line. If we look at the data, it looks like we still have a slope which is a little bit high, so maybe I can take this down to 0.75. 345, that made it much worse, but if I at the same time take this down to -30, now it has improved from 300 something to 200 something. From this little experiment, we see this particular thing, that the residuals will all depend on how I pick B1 and B2. That is, the residuals will all depend on my choice of trend line. That means that RSS, which is the sum of square of these residuals, will depend on how I pick B1 and B2. If I change B1 and B2, I will also change RSS. That idea is all we need to describe the least squares principle. So the least square principle is simply this. Select B1 and B2, that is, select the slope and the intercept of the trend line such that RSS is as small as possible. Remember, we use RSS as a measure of fit, where we've said that the smaller the RSS is, the better is the fit. So it kind of makes sense trying to minimize RSS. Mathematically, we then have this problem. We need to minimize a function, that is the RSS function, which we know depends on B1 and B2. So that is the least squares problem, minimized by selecting B1 and B2 RSS. And remember, RSS is just defined as the sum of the squared residuals. So this particular mathematical problem is called the least squares problem. It's a purely mathematical optimization problem, and it can be solved by using standard mathematical techniques. You take the derivatives and set them to 0 and so on. But we're not going to look at that in this lecture. So the least squares principle is this. Play around with these two cells. Just try to manipulate these two cells in order to make this cell as small as possible. Now, it's kind of a long and kind of nasty and maybe a little bit fun in the beginning, but eventually it gets kind of tedious trying to manipulate these two numbers so that we get the smallest possible value for this. Fortunately, Excel has a built-in function where it basically does the job for you. It plays around with these two values and it has as a goal trying to minimize this one. To do this particular thing, you need what's called an add-in, and the name of the add-in is called the solver. So what you do is you go to File, Options, then you go to here at the left, you go to Add-ins, and then you can go to Manage Excel Add-ins, Go. What you need to do is just make sure that this solver add-in is checked. If you want to do econometrics using Excel, you should also check the analysis tool pack. Okay, so then that will show up under the data, and here is the solver. So if we click the solver, it says it looks like this. First, it has an objective. That's the thing that you want to do something with. And my objective cell is precisely this E13. That's the objective. And I don't want to maximize this, but I want to minimize it. So I want to try to make this as small as possible. Next, Excel asks you which cells am I allowed to manipulate. And the cells that Excel can play around with are these two, B1 and B2. And the last thing you have to do is to unclick that one because we don't have any such constraints. Then when you click solve, Excel will just start playing around with these and try to figure out the minimum. Solve, keep solver solution, okay, and here it has done it. It figured out that the smallest value it can get to for RSS is 159.28. And it got to that value by picking these values for B1 and B2. So that means that if I now change any of these two values, RSS will increase. It doesn't matter which direction I change them. So let's try to change something here. If I change this to 0.60, just slightly, 0.61 instead, 159.27, yeah, it goes up a lot. Control Z to take it back. If I change it to 0.59, it will go up as well. So this is indeed the solution to the least squares problem. You may recognize these two numbers because we've seen them in previous lectures. They are precisely the OLS estimates. So if I do this again, I type here B2, B1, highlight these cells, and I write linest known y's, known x's, true, that's same thing as 1, and false, that's same thing as 0. Shift Control Enter, you see that you get exactly these same values. So what we learned from this little experiment is that the solution to the least square principle, the solution to the least square problem, and that is the value that will minimize RSS, is found by the OLS formula. So the solution is precisely these two that we've seen before, the OLS formula. So that answers the question, where do these numbers come from? Why does Excel, for example, pick this as its trend line, as the best fit? And the answer is because that's the trend line which has the smallest possible value for RSS. You cannot find a trend line with a smaller value of RSS. That's what the OLS formula is derived from. So to review, the least square principle is find a trend line such that RSS is minimized. That gives rise to a mathematical problem which is called a least squares problem. You can analytically solve this problem and you can prove that the solution is precisely what's in front of us here, the OLS formula. And we have illustrated that now in Excel as well, that the OLS formula, the OLS values for B1 and B2 are indeed the values that will minimize RSS.